Well, hey, I got a problem that's really killing me right now. It was first posted by a gentleman by the name of Benjamin Cung. I want to give him credit. He posted this first, not me. But now I can't find his work anymore. And I just want to compare my work with his and see how things are going. It's a nice little problem. And again, he posted it, and then all of a sudden it's like the video disappeared. So anyway, I went through this process and ended up with a recursive definition of this function. And I would love to know what his results were. What we have right here is a summation of floor functions of logarithms base 10. Now, logarithms are kind of natural floor functions because they don't grow very fast. So you can expect a large number of logarithms to share the same floor, and that's kind of what this analysis reveals. This lemma right here is very, very handy. Again, this is log base 10, but log base 10 of n is equal to m if n is in this interval. And notice how we decrement the next highest power. A simple example here would be if m were equal to 2, this would be 100. And of course, we know log base 10 of 100 is 2. And that would run all the way out to 999. You'd have to reach 1,000 before the floor would change to 3. Okay, so there's a long range of natural numbers that have the very same floor. And so this lemma is quite useful. Now, k equals 1 is a fairly straightforward case. Log base 1, of course, is 0. Log base anything of 1 is 0. And then all the way up to 9, you would have a floor of 0. So this is all equal to 0, right? All the way up to 9. Log base 9 is a number close to 1, but it's still less than 1 and above 0. So its floor is 0. Now, right here for k equals 2, we included this log 1, log 2, all the way up to log 9, and that's 0. And now we start up at log 10 all the way up to log 99 based on this lemma. And now this is a little tricky. From 10 to 99 is actually 90 values, and all 90 of those values have a floor of 1. Okay, so we're going to get 90 for this step. And I don't want to bore you too much, but it's recursive. You can see how it depends on previous results, and I tried to convey that with the ellipsis here. Now you get to log base 10 of 100, and you run all the way up to 999. Again, that's consistent with this lemma and sort of consistent with these indices of these summations right here. So from 100 to 999 is actually 900 numbers. You got to be a little careful with that. It seems like it might be 899, but it is 900 numbers. But all of those numbers starting at 100, log base 10 of 100 is 2 all the way up to 999. So you get the 2 times the 900 times the plus the 90, which was the previous one, and that's where this recursion comes in. And I'll let you go through this last step. But anyway, we get a recursive definition. It's very interesting. If once you get the ball rolling, you can work like this. Now there may be a closed form, which is what Mr. Cung may have been shooting for. I don't know, but I decided to define it recursively. And once you get the first one, you can get the next one, and so on and so forth. But I listed a few examples right here for 2, 3, and 4, and I thought it was convenient to represent this as a function of k. But anyway, I hope he gets a chance to look at it. We can compare results, and I want to see if I did it right or if different approaches. Again, there may be a closed form where each term just depends explicitly on k. That seemed a little messy to me, so I stuck to this recursive definition. Okay, hope you guys enjoy.